Hello there, and welcome to The Sleepy Scientist. Tonight we're going to take a slow and gentle journey through the quiet depths of the universe, exploring one of the most beautiful motions in all of astronomy, the slow and graceful spinning of galaxies. Across the cosmos, enormous islands of stars turn silently through space. Spiral arms sweep across the darkness, billions of suns moving together in a calm cosmic dance that has been unfolding for billions of years. But this raises a simple and fascinating question. Why do galaxies spin? What first set these enormous structures in motion? And why do they continue turning even today? So get comfortable, relax your mind, and let the quiet story of the universe unfold. And if you enjoy calm explorations of space and science like this, consider subscribing to the channel and joining us for more peaceful journeys through the cosmos. Let's begin. Have you ever looked up at the night sky and imagined the galaxy we live in? Not just the stars you can see with your eyes, but the enormous structure they are part of. A vast spiral of light stretching across 100,000 light years, slowly turning through the darkness of space. Our galaxy, the Milky Way, is not standing still. It is spinning. Every star within it, including our Sun, is quietly moving along a long orbit around the galactic center. Right now, at this very moment, our entire solar system is traveling through this galaxy at around 800,000 kilometers per hour. And yet, we feel nothing at all. The motion is so smooth, so enormous in scale, that it feels perfectly still. But if galaxies are made of billions or even trillions of stars, scattered across immense distances, a natural question begins to appear. Why do galaxies spin at all? What first set these vast systems in motion? And why has that motion continued for billions of years? When we look out into the universe with powerful telescopes, we discover that galaxies come in many shapes and sizes. Some are large spirals, with graceful arms curving outward like giant cosmic pinwheels. Others are smooth elliptical galaxies, glowing softly like giant spheres of starlight. Some are irregular, chaotic clusters of stars and gas. But among the most beautiful and recognizable are the spiral galaxies. Galaxies like our own. Their arms wind gently around a bright central core, forming patterns that stretch across tens of thousands of light years. And as we observe them, one thing becomes clear. They are rotating. The entire structure is slowly turning. Stars orbit the center. Clouds of gas drift along the spiral arms. Even enormous regions of dust follow the same quiet rotation. It is a slow motion, taking hundreds of millions of years for a single orbit to complete. For example, our Sun takes about 230 million years to circle the center of the Milky Way just once. When the dinosaurs walked on Earth, our solar system was in a completely different part of the galaxy. And since that time, we have travelled only a small fraction of one orbit around the galactic center. Galaxies move on timescales so vast that their motion is almost impossible to notice within a human lifetime. But astronomers can measure this motion by studying the light coming from distant stars. When stars move toward us, their light shifts slightly toward the blue end of the spectrum. When they move away from us, the light shifts toward red. By measuring these tiny shifts, astronomers can determine the speed and direction of stars across a galaxy. And what they discovered was remarkable. Stars on one side of a galaxy are moving toward us, while stars on the opposite side are moving away. This pattern reveals that the entire galaxy is rotating, a giant cosmic wheel slowly turning through the darkness of space. But this discovery raised an even deeper mystery. Because when scientists calculated the speeds of stars orbiting galaxies, something didn't quite make sense. Stars near the outer edges of galaxies were moving much faster than expected. According to the laws of gravity, stars farther from the center should move more slowly. Just like planets in our solar system, Mercury orbits the Sun very quickly, completing its path in only 88 days. But Neptune, far out in the cold outer reaches of the solar system lower, takes 165 years to complete a single orbit. The farther away a planet is, the slower it moves. At least, That is what gravity predicts. So astronomers expected the same pattern in galaxies. Stars near the galactic centre should move quickly, while stars far away should drift along more slowly. But when they measured the speeds, that is not what they found. Instead, stars far out in the galaxy were moving almost just as fast as stars near the centre. It was as if something invisible was adding extra gravity, holding the galaxy together. Something that could not be seen, but clearly had mass. This strange discovery led scientists to one of the most fascinating ideas in modern astronomy: the existence of dark matter. Dark matter does not emit light. It does not glow like stars or reflect light like planets. It cannot be seen with telescopes. And yet, its gravity appears to shape the motion of galaxies. Most astronomers now believe that galaxies are surrounded by enormous halos of dark matter, invisible spheres extending far beyond the visible stars. These halos contain far more mass than the stars themselves. In fact, only about 15% of a galaxy's mass may be made of ordinary matter. The rest could be dark matter. This invisible structure acts like a gravitational skeleton, holding the galaxy together and helping it maintain its rotation. Without dark matter, galaxies might not spin the way they do. Their outer stars might drift away into space. But even dark matter does not fully explain how galaxies first began to spin. To understand that, we need to travel back much further in time, back to the early universe, a time before galaxies existed, a time when the cosmos was filled mostly with hot gas and faint radiation. After the universe began expanding, tiny variations in density appeared in the cosmic gas. Some regions were slightly denser than others. Gravity slowly pulled these denser regions together. Over millions of years, gas gathered into enormous clouds. These clouds grew larger and larger, eventually forming the first galaxies. But these clouds were not perfectly still. Small motions were already present in the early universe. Tiny irregular movements, almost like gentle currents in a vast cosmic ocean. As gravity pulled gas inward, these small motions became amplified. A cloud that had even a slight rotation would begin to spin faster as it collapsed. This happens because of a simple physical principle known as conservation of angular momentum. It may sound complicated, but the idea is actually very familiar. Imagine a figure skater spinning on ice. When the skater stretches their arms outward, they spin slowly. But when they pull their arms close to their body, they spin faster. Nothing new is pushing them. They simply become smaller, and their rotation speeds up. The same principle applies to collapsing clouds of gas in space. As gravity pulls the gas inward, the cloud becomes more compact. And if the cloud had even the tiniest amount of rotation to begin with, that rotation speeds up. Over time, the cloud flattens into a rotating disk. Stars begin to form inside it, and eventually, a spinning galaxy is born. This is why so many galaxies have disk shapes. Their rotation causes material to spread outward into a wide spinning plane. Within that plane, spiral arms form as waves of star formation ripple through the disk. And over billions of years, the galaxy continues its quiet rotation. But the story of galactic motion does not end there. Because galaxies do not exist in isolation. They interact with one another. They pass near each other. Sometimes they collide. Sometimes they merge. These encounters can dramatically change the way galaxies spin. When two galaxies pass close together, their gravity pulls on each other. Stars shift their paths. Gas clouds compress, igniting bursts of star formation. Spiral arms stretch and twist. And sometimes, after millions of years of slow gravitational interaction, the two galaxies merge into one larger galaxy. During these mergers, the original rotations of both galaxies combine in complex ways. The final galaxy may spin differently than either of its parents. It may become an enormous elliptical galaxy, its stars moving in many different directions. Or it may settle into a new rotating disk. The universe is full of these slow cosmic interactions, galaxies gently reshaping each other over billions of years. Even our own galaxy is part of this story. Billions of years from now, the Milky Way will collide with the nearby Andromeda Galaxy. The two great spirals will slowly merge, forming a single larger galaxy. Stars will drift into new orbits. New patterns of motion will appear. But even during that dramatic event, the overall rotation of the merged galaxy will continue. Because once motion begins on these enormous scales, it rarely stops. Space is almost completely empty. There is very little friction to slow things down. Stars move along their orbits freely, guided only by gravity. And so galaxies continue spinning for billions of years. A quiet dance of stars, unfolding slowly across the universe. And when we look up at the night sky, we are part of that motion too. Our planet orbits the Sun. Our Sun orbits the center of the Milky Way. The Milky Way itself moves through space within a cluster of galaxies. And the entire universe continues expanding. Everything is moving. Everything is part of a larger cosmic flow. Yet from our small place on Earth, Naka, beneath the calm night sky, the universe appears still. The stars seem fixed. The sky feels quiet. But hidden within that stillness is motion on an unimaginable scale. Galaxies slowly turning, stars tracing vast circles through space, and the quiet spinning of the cosmos continuing, far beyond the limits of human time. If you could somehow travel far above the Milky Way, rising slowly out of the galaxy and looking back from deep space, you would begin to see its true shape. From Earth, the galaxy appears as a faint glowing band stretching across the night sky. But that soft band of light is only the edge of something far larger. Seen from afar, the Milky Way would look like a vast spiral, a rotating disk of stars, gas and dust slowly turning through the darkness. 4 long spiral arms curl outward from a bright central bulge. Between those arms lie enormous lanes of interstellar dust, dark rivers drifting across the galaxy. And scattered throughout the spiral arms are billions of stars, each following its own quiet orbit around the center. At the very heart of the Milky Way lies something extraordinary, a supermassive black hole. This object, known as Sagittarius, a star, contains the mass of roughly 4 million suns compressed into a region smaller than our solar system. Although it is invisible itself, its gravity strongly influences the motion of nearby stars. Stars near the center of the galaxy move incredibly fast, some completing full orbits in only a few decades. Astronomers have been able to track these stars carefully, watching them whip around the unseen black hole like glowing fireflies circling an invisible lantern. But even though this black hole is powerful, it does not control the motion of the entire galaxy. Most of the Milky Way's rotation is governed by the combined gravity of billions of stars, along with enormous halos of dark matter surrounding the galaxy. The rotation of the galaxy spreads that gravitational influence across the entire disk. Every star contributes a tiny piece of the gravitational field that holds the galaxy together. Together, they form a delicate balance. Gravity pulls inward. Motion carries stars forward along their orbits. And the result is a stable rotating system that can persist for billions of years. But galaxies are not perfectly smooth structures. They contain waves and patterns that ripple slowly through their disks. One of the most beautiful of these patterns is the spiral arm. At first glance, spiral arms might seem like fixed structures made of specific stars, but in reality, they behave more like traffic waves moving through a highway. Imagine cars traveling along a busy road. Even though each car moves forward, areas of congestion can form where vehicles slow down. Those dense clusters of cars can appear to move backward along the road, even though the cars themselves continue forward. Something similar happens inside spiral galaxies. The spiral arms are regions where stars and gas become temporarily crowded together. As gas clouds pass through these denser regions, they compress. That compression triggers bursts of star formation. New stars ignite. Bright clusters appear, and the spiral arms glow with fresh starlight. But the individual stars inside those arms do not stay there forever. They continue orbiting the galaxy, gradually drifting out of the arm while new stars enter it. The spiral pattern itself slowly moves through the galaxy like a wave. This creates the graceful spiral structures we see in telescope images. long glowing arms filled with young blue stars, winding outward across the rotating disk. These spiral arms also help shape the motion of gas clouds inside the galaxy. When gas flows through an arm, it becomes compressed and heated. Shock waves ripple through the clouds, and those disturbances can trigger the collapse of dense regions that eventually form new stars. Over millions of years, these newborn stars illuminate the spiral arms, making them appear brighter than the surrounding regions. In this way, the rotation of a galaxy is closely connected to the birth of new stars. Motion shapes structure. Structure shapes star formation. And star formation helps define the appearance of the galaxy itself. But the spinning of galaxies is not always smooth and orderly. Sometimes gravity creates dramatic distortions. Nearby galaxies can tug on each other as they pass. Their spiral arms stretch outward like long tidal tails. Stars are flung into new orbits. Gas clouds collide. New waves of star formation ignite. These encounters can transform the shapes of galaxies entirely. A spiral galaxy may become warped or stretched. Its arms may twist and bend under gravitational forces. Over long periods of time, these interactions can even erase the spiral structure completely. When two large galaxies merge, their ordered rotation may become scrambled. Stars begin moving in many different directions rather than following neat circular paths. The resulting galaxy may become an elliptical galaxy, a vast glowing sphere of stars moving in complex orbits. Elliptical galaxies often contain very little gas and dust. Without large reservoirs of gas, few new stars are formed. The galaxy slowly ages as its existing stars grow older and dimmer. But even elliptical galaxies still carry traces of rotation. The motion of stars within them reflects the long history of gravitational interactions that shape their formation. In the vast scale of the universe, galaxies are constantly influencing one another. They gather in clusters containing hundreds or thousands of galaxies. These clusters themselves rotate slowly and drift through space. Gravity binds them together into enormous cosmic structures. Between the galaxies within these clusters flows extremely hot gas. This gas glows faintly in X-rays, revealing the presence of massive gravitational forces at work. And surrounding the entire cluster lies even more dark matter, forming gigantic halos that extend far beyond the visible galaxies. The universe on its larger scales resembles a complex web. Galaxies gather along long filaments stretching across hundreds of millions of light years. Where these filaments intersect, enormous clusters form. Between them lie vast cosmic voids where few galaxies exist. Even these immense structures carry subtle motions. Galaxies drift along the filaments. Clusters slowly rotate and merge. The entire cosmic web evolves over billions of years. Rotation appears everywhere we look in the universe. Planets spin, stars rotate. Galaxies turn. Even enormous clusters of galaxies contain traces of rotational motion. This widespread presence of rotation suggests something fundamental about how structures form in the universe. Small motions present in the early cosmos became amplified as gravity gathered matter together. What began as tiny irregular flows in the primordial gas eventually grew into the vast rotating systems we see today. The universe took those faint beginnings and slowly sculpted them into galaxies filled with spinning stars. And within one of those galaxies, orbiting one ordinary star among billions, sits a small blue planet quietly travelling along its own path through space. Our world is part of the same grand cosmic motion. The Earth spins on its axis. The Earth orbits the Sun orbits the centre of the Milky Way. And the Milky Way itself moves through the universe among countless other galaxies. Everything is in motion, even when it feels perfectly still. If we slow down our imagination for a moment and picture the universe as it was long ago, the story of spinning galaxies becomes even more fascinating. Nearly 14 billion years ago, the universe was very different from the calm cosmic landscape we see today. There were no galaxies, no stars, no planets, only an expanding sea of hot gas and radiation filling every direction. Matter was spread almost evenly throughout space, but not perfectly. Tiny fluctuations existed. Some regions were slightly denser than others. These differences were incredibly small, sometimes only one part in 100,000. Yet those tiny irregularities would eventually shape the entire structure of the universe. Gravity began working on those small differences. Where matter was slightly denser, gravity pulled more gas inward. As more matter gathered, the gravitational pull grew stronger. Slowly, very slowly, enormous clouds of gas began to form. These clouds stretched across vast regions of space. They were not perfectly smooth or still. Subtle motions were already present within them, gentle flows and currents left over from the early expansion of the universe. When gravity began pulling these clouds inward, those tiny motions became more important. Even the smallest sideways movement would begin to grow as the cloud collapsed. Imagine a massive cloud of gas slowly shrinking under gravity. If the gas were falling perfectly straight inward from every direction, the cloud might collapse into a simple sphere. But if there is even a slight sideways motion in the gas, something interesting happens. The material begins to swirl. As the cloud becomes smaller, that swirling motion speeds up. This happens because of a fundamental rule of physics called conservation of angular momentum. It is the same principle that causes a spinning figure skater to rotate faster when they pull their arms inward. As the skater's body becomes more compact, the rotation speeds up. In the same way, a collapsing cloud of gas spins faster as it shrinks. Over time, that spinning motion flattens the cloud into a rotating disk. Gas settles into a thin plane where most of the motion takes place. And within that rotating disk, the first stars begin to form. These early stars were very different from the stars we see today. They were likely enormous, hundreds of times more massive than the Sun. They burned extremely hot and bright, using up their nuclear fuel quickly. After only a few million years, many of them exploded as powerful supernovae. These explosions scattered heavier elements throughout the surrounding gas. Elements like carbon, oxygen, and iron, the ingredients that would later become part of planets and life. With each generation of stars, the universe became richer in these elements. New clouds of gas formed new stars. New galaxies slowly took shape. And through all of this, the gentle rotation that began in those early gas clouds continued to shape the structure of galaxies. The disks of spiral galaxies are the natural result of this long process. Rotation spreads matter outward along a flat plane. Stars settle into orbits around the galactic center. Gas clouds drift along those same paths, and spiral patterns emerge as waves ripple through the rotating disk. But galaxies are not rigid objects like spinning wheels. They're dynamic systems filled with billions of independent stars. Each star moves under the influence of gravity, tracing its own path through to the galaxy. Some stars follow nearly circular orbits. Others move along slightly stretched elliptical paths. Some travel above and below the galactic disk. Yet despite this complexity, the overall rotation of the galaxy remains stable. The combined gravitational pull of billions of stars keeps the entire system bound together. Dark matter plays a crucial role in maintaining this stability. Without the extra gravity provided by dark matter halos, galaxies might not be able to hold on to their fast-moving outer stars. Those stars could drift away into intergalactic space. Instead, the invisible mass surrounding galaxies provides additional gravitational support. It acts like an enormous unseen structure, extending far beyond the visible stars. Astronomers cannot see dark matter directly, but they can detect its presence through its gravitational effects. When they measure how fast stars move in galaxies, the results reveal far more mass than can be accounted for by visible stars and gas. Something unseen must be contributing additional gravity. That mysterious substance is what scientists call dark matter. It does not interact with light. It does not glow or absorb radiation. Yet it appears to make up most of the matter in the universe. In many ways, galaxies are like glowing islands embedded within vast halos of dark matter. The visible stars form the bright central regions we can see with telescopes, but surrounding them are enormous invisible structures stretching far into space. These halos help guide the motion of galaxies and shape their formation. In fact, many astronomers believe that dark matter halos formed first. Gas later fell into those halos, forming rotating disks where stars could ignite. Without dark matter, the formation of galaxies might have been very different. perhaps they would not have developed the elegant spiral structures we observe today. Instead, the universe might have looked far more chaotic. Yet even with dark matter guiding their formation, galaxies still experience constant change. They are never truly finished evolving. New stars continue forming within their spiral arms. Old stars gradually grow older and dimmer. Gas clouds move through the disk, collapsing in some places and dispersing in others. And occasionally, galaxies encounter one another. When two galaxies approach, their gravitational fields interact long before the galaxies actually touch. Stars begin shifting into new orbits. Gas clouds stretch into long tidal streams. Over millions of years, the galaxies may spiral toward each other and merge. These mergers can dramatically reshape galaxies. A spiral galaxy might lose its delicate arms during a collision. The rotating disk may become scrambled as stars scatter into new directions. After the merger settles, the result may be a massive elliptical galaxy filled with stars moving in many different paths. But even then, traces of the original rotations remain hidden within the motion of those stars. The universe rarely erases motion completely. Instead, it redistributes it. Rotation becomes mixed and transformed, but the underlying energy continues flowing through the system. This constant reshaping of galaxies has been happening for billions of years. The Milky Way itself has likely absorbed many smaller galaxies during its history. Streams of stars discovered in our galaxy appear to be the remnants of ancient galactic mergers. Long ribbons of stars drifting across the halo of the Milky Way, the faint echoes of past encounters. Even now, our galaxy continues interacting with nearby companions. Several small satellite galaxies orbit the Milky Way, slowly being pulled apart by tidal forces. Their stars are gradually joining the larger structure of our galaxy. These slow cosmic interactions contribute to the ongoing evolution of galaxies. Yet through all these changes, the overall rotation of galaxies often survives. The giant cosmic dance continues. Stars orbit the galactic center. Gas clouds drift through spiral arms, and the vast disk of the galaxy slowly turns through the darkness of space. On human timescales, this motion is almost impossible to notice. A full rotation of the Milky Way takes hundreds of millions of years. Entire civilizations rise and fall during only a tiny fraction of that time. But across cosmic history, galaxies have been spinning quietly for billions of years. Their rotation is one of the great rhythms of the universe. A motion that began with tiny fluctuations in the early cosmos and continues even now across vast distances of space. If we could somehow watch a galaxy over an incredibly long stretch of time, millions or even billions of years, the motion would slowly become visible. Stars would glide along enormous circular paths. Spiral arms would shift gently around the center. Clouds of gas would drift like slow-moving weather patterns across the galactic disk. It would resemble a vast celestial whirlpool, turning almost imperceptibly in the dark ocean of space. But galaxies are not perfectly ordered systems. Within their rotating disks, stars and gas experience constant gravitational interactions. Every star pulls slightly on every other star. Gas clouds collide and merge. Shock waves ripple through the interstellar medium. Over immense spans of time, these interactions gradually reshape the internal structure of galaxies. One of the most interesting effects occurs in the central regions. At the heart of many galaxies lies a dense concentration of stars known as the galactic bulge. This region contains some of the oldest stars in the galaxy. Their orbits are often more chaotic than those of stars in the disk. Instead of moving in nearly circular paths, they travel along elongated and tilted orbits. The result is a thick, rounded cluster of stars surrounding the galactic center. Inside this crowded environment, gravitational interactions happen more frequently. Stars pass relatively close to one another. Their paths are slowly altered by these encounters. Over billions of years, the bulge becomes a dynamic and complex system of stellar motion. Surrounding the bulge is the galactic disk, the wide rotating structure where spiral arms form. This disk is where most of the galaxy's gas and dust reside, and it is where new stars continue to be born. The rotation of the disk helps organize this material into patterns. Gas clouds drift through the spiral arms, compressing and collapsing into clusters of young stars. These newly formed stars often shine bright blue, illuminating the arms of the galaxy. But the spiral arms themselves are not permanent features. They slowly change shape over time. Some arms fade while others grow stronger. Sometimes, new spiral patterns emerge as gravitational waves ripple through the disk. In certain galaxies, a long bar-shaped structure forms across the centre. This feature is known as a galactic bar. It consists of stars moving along elongated orbits that stretch across the central region. Bars are surprisingly common in spiral galaxies. In fact, our own Milky Way appears to contain one. Astronomers believe that galactic bars play an important role in the evolution of galaxies. The gravitational forces within the bar can funnel gas toward the centre of the galaxy. As gas flows inward, it may feed the supermassive black hole at the core. This can trigger energetic activity, causing the central region to glow brightly as matter spirals into the black hole. At other times, the inflowing gas may simply fuel new bursts of star formation near the centre. The bar acts like a cosmic conveyor belt, slowly transporting material across the galaxy. But even these large structures are not permanent. Over billions of years, bars may weaken or dissolve as gravitational interactions reshape the galaxy. New bars may later form as the galaxy continues evolving. Rotation remains the underlying motion tying all these processes together. Without rotation, the disk structure of spiral galaxies might never exist. Stars would move in many random directions, creating more spherical shapes like those seen in elliptical galaxies. Instead, rotation organizes the motion of stars into a flattened system where ordered patterns can develop. Yet the rotation of galaxies is not perfectly rigid like a spinning wheel. Different parts of a galaxy rotated at different speeds. Stars closer to the center complete their orbits faster than those farther out. This phenomenon is known as differential rotation. Because of differential rotation, the spiral arms of galaxies cannot simply be fixed structures made of the same stars. If they were, the arms would gradually wind tighter and tighter as the inner regions rotate faster than the outer regions. Over time, the arms would become so tightly wrapped that they would disappear. But this is not what we observe. Instead, spiral arms remain relatively stable. This led astronomers to propose that spiral arms are not fixed collections of stars. Rather, they're density waves moving through the disk. In these waves, stars and gas temporarily bunch together as they orbit the galaxy. As material passes through the wave, it slows slightly and becomes compressed. Gas clouds collapse, forming new stars. Then the stars continue moving onward, leaving the spiral arm behind. The arm itself remains as a wave pattern that continues travelling through the disk. This elegant mechanism explains how spiral structures can persist for billions of years. It also helps explain why spiral arms often appear bright with young stars. The compression of the gas within the density wave triggers star formation, lighting up the arm as fresh stars ignite. But beyond the visible disk of the galaxy lies another important region, the galactic halo. This is a vast spherical region surrounding the galaxy. It contains old stars, globular clusters, and enormous amounts of dark matter. And the halo extends far beyond the bright spiral arms. Some stars in the halo travel along highly elongated orbits that carry them thousands of light years above and below the galactic plane. These stars move in complex paths influenced by the galaxy's overall gravitational field. The halo also contains ancient star clusters known as globular clusters. Each of these clusters may contain hundreds of thousands of tightly packed stars. Many of them formed early in the history of the galaxy. They orbit the galactic center like distant satellites, slowly circling the galaxy over hundreds of millions of years. The halo serves as a kind of outer boundary for the galaxy's gravitational influence. Within it, the dark matter halo dominates the total mass of the galaxy. Its gravitational pull helps keep the outer stars bound to the galaxy despite their high speeds. Without this invisible structure, galaxies might gradually lose their outer stars over time. Instead, the dark matter halo provides the additional gravity needed to maintain the galaxy's rotation, and so the galaxy continues spinning. Stars orbit quietly around the center. Gas flows through spiral arms. New stars ignite while older ones slowly fade. All of it unfolding across enormous stretches of time. From our small vantage point inside the Milky Way, this grand rotation is almost impossible to perceive directly. We see only a tiny portion of the galaxy around us. The full spiral structure remains hidden by clouds of interstellar dust and the vast distances between stars. But through careful observation and measurement, astronomers have slowly pieced together the larger picture. They have mapped the motion of stars, measured the rotation of distant galaxies, and revealed that spinning galaxies are one of the most common and beautiful structures in the universe. Across the cosmos, billions of galaxies turn slowly in the darkness, each one carrying billions of stars along graceful orbits that have lasted for billions of years. And within one of those galaxies, orbiting one ordinary star, our small world continues its own quiet motion through the vast rotating universe. If we continue drifting outward in our imagination, leaving the Milky Way behind and looking deeper into the universe, we begin to notice that galaxies are rarely alone. They gather together. Small groups of galaxies orbit one another, bound by gravity. Our own galaxy belongs to a modest collection called the Local Group. Within this group are more than 50 known galaxies. Some are large spirals like the Milky Way and Andromeda. Others are tiny dwarf galaxies containing only a few billion stars. These galaxies slowly move around one another, tracing enormous paths through space. The Milky Way and Andromeda are the two largest members of this group, and over billions of years, their gravity has been quietly pulling them toward one another. Right now, they're approaching at a speed of roughly 100 kilometers per second. This slow approach is almost impossible to notice within a human lifetime. But across cosmic time, it will eventually lead to one of the most dramatic events in our region of the universe. The two galaxies will collide. Yet the word collision can be misleading. Even though galaxies contain billions of stars, the distances between those stars are so enormous that direct stellar collisions are extremely unlikely. Instead, the galaxies will pass through each other like two enormous swarms of glowing fireflies. Their gravity will distort their shapes. Spiral arms will stretch and twist. Long streams of stars will arc outward into space like tidal waves. For a time, the sky within those galaxies will look extraordinary. If any planets still exist in our solar system billions of years from now, observers on those worlds might see Andromeda growing larger and brighter in the sky. Eventually, its spiral arms could stretch across huge portions of the heavens. Over hundreds of millions of years, the two galaxies will merge. Their stars will settle into new orbits within a single, larger galaxy. Astronomers believe the final result will likely be an elliptical galaxy, a massive sphere of stars moving along complex paths. Yet even after such a dramatic event, motion will remain. The merged galaxy will continue rotating in its own way. The original spins of both galaxies will blend together, creating a new pattern of movement among the stars. Rotation is rarely erased entirely. Instead, it is transformed and redistributed. This pattern repeats across the universe. Galaxies grow larger by merging with smaller companions. Each encounter reshapes the galaxy's structure. Some mergers trigger intense bursts of star formation. Gas clouds collide and compress, forming clusters of brilliant young stars. Other mergers strip galaxies of their gas, leaving behind older populations of stars that slowly fade over time. But through all these changes, gravity continues guiding the motion of stars, and the overall rotation of galaxies persists across billions of years. When astronomers observe distant galaxies with powerful telescopes, they often see evidence of these ancient interactions. Some galaxies display long tidal tails, faint streams of stars stretching far beyond the main disk. Others appear distorted or warped, their shapes still recovering from past encounters. Some galaxies are caught in the act of merging, their spiral arms tangled together like strands of cosmic smoke. These observations reveal that the universe is constantly evolving. Galaxies are not permanent objects. They're dynamic systems that grow, merge, and change over time. Yet their rotation remains one of the most enduring aspects of their motion. Across the observable universe, billions of galaxies spin quietly in the darkness, each one a vast rotating system containing billions of stars. And when astronomers measure the motion of galaxies across large regions of space, they notice something even more fascinating. Entire clusters of galaxies can rotate. These clusters contain hundreds or even thousands of galaxies bound together by gravity. Within them, galaxies drift along enormous orbits around the cluster's center of mass. Between the galaxies lies extremely hot gas, heated to millions of degrees. This gas emits faint X-rays that astronomers can detect with specialized telescopes. The motion of galaxies within clusters helps scientists estimate the total mass of these enormous structures. Once again, the calculations reveal something surprising. The visible galaxies and gas account for only a fraction of the total mass needed to hold the cluster together. Most of the mass appears to be dark matter, invisible, yet exerting powerful gravitational influence. Dark matter halos extend far beyond the visible edges of galaxies and clusters. They form the scaffolding upon which the large-scale structure of the universe is built. Galaxies form within these halos. Clusters form where many halos gather together, and the entire cosmic web slowly evolves under the influence of gravity and expansion. Rotation appears even within these enormous structures. Small initial motions present in the early universe become amplified as matter gathers together. Just as tiny rotations in collapsing gas clouds led to spinning galaxies, subtle motions within larger regions may lead to the slow rotation of galaxy clusters. The universe seems to favor motion. It rarely creates perfectly still systems. Instead, matter flows, drifts, and rotates across every scale we observe. From spinning planets to rotating galaxies, motion is woven into the fabric of cosmic structure. Even the Earth beneath our feet participates in this great dance. Our planet spins once every 24 hours. This rotation gives us day and night. It shapes our weather systems and ocean currents. Without it, life on Earth would look very different. The Earth also orbits the Sun once every year. The Sun itself travels around the center of the Milky Way, and the Milky Way moves through space within the local group. All of these motions combine into a vast cosmic journey. Yet from our everyday perspective, the universe feels still. When we look up at the night sky, the stars seem fixed in place. They rise and set each night as the Earth rotates. But the deeper motions of the cosmos unfold on timescales far beyond human experience. Galaxies spin so slowly that millions of years pass before noticeable changes occur. Clusters drift through space across billions of years. The universe evolves patiently. Its movements are quiet and gradual. And perhaps that is part of the beauty of it all. A universe filled with motion, yet calm enough that we can pause, look up at the stars and wonder how such vast systems came to spin in the first place. If we imagine watching the universe for long enough, longer than any human lifetime, longer than the entire history of civilization, the slow spinning of galaxies would eventually reveal itself like a quiet cosmic ballet. Stars would trace graceful arcs through space. Spiral arms would drift gently around their galactic centers. Clouds of gas would stretch, compress, and ignite new generations of stars. All of it happening so slowly that the galaxy itself would seem to breathe over hundreds of millions of years. But the story of spinning galaxies is not only about motion, it is also about balance. Gravity is constantly pulling matter inward. Stars, gas, and dark matter all feel the attraction toward the galaxy's center. If gravity were the only force at work, galaxies might collapse inward, becoming smaller and denser over time. Yet the stars within galaxies are not simply falling straight toward the center. They're moving sideways as they orbit. This sideways motion creates what astronomers call centrifugal balance. As a star travels along its orbit, its motion continually carries it forward. Gravity pulls it inward, while its motion carries it around the center. The result is a stable orbit, a delicate balance between inward pull and forward motion. This same principle keeps planets orbiting stars. The Earth is constantly being pulled toward the Sun by gravity, but because it is also moving sideways through space, it continues circling the Sun instead of falling directly into it. Galaxies operate under the same fundamental laws. Every star within a galaxy follows a path determined by the combined gravitational influence of all the matter around it. The paths may be nearly circular or slightly elliptical. Some stars drift above or below the disk. Others follow more chaotic routes through the galactic bulge. But taken together, these motions produce the large-scale rotation that defines spiral galaxies. And because space contains very little friction, these motions can continue almost indefinitely. There's nothing in the near vacuum of interstellar space to significantly slow the motion of stars. Once a galaxy begins rotating, that rotation can persist for billions of years. This persistence of motion is another result of a fundamental law of physics. Objects in motion tend to remain in motion unless acted upon by an external force. In the emptiness of space, such forces are rare. Stars glide along their orbits with remarkable stability. Only the slow gravitational influence of other stars, gas clouds, and nearby galaxies gradually alters their paths. Even these changes happen slowly. A star might take millions of years before its orbit shifts noticeably, and so galaxies remain stable rotating systems across immense spans of time. Yet despite this stability, galaxies are far from static. Inside the rotating disk, countless small interactions constantly reshape the galaxy's structure. Gas clouds collide and fragment. New stars form in clusters. Massive stars explode as supernovae, releasing enormous amounts of energy. These explosions send shock waves through nearby gas clouds, triggering new rounds of star formation. Over time, the galaxy becomes a dynamic ecosystem of stellar birth and death. Young stars shine brightly for millions of years. Older stars grow cooler and dimmer. Some collapse into white dwarfs, neutron stars, or black holes. Each generation of stars enriches the galaxy with heavier elements. The rotation of the galaxy helps distribute this material across the disk. Gas flows along spiral arms. Shock waves ripple through star-forming regions. Gravity guides matter into new patterns. Slowly, the galaxy evolves. And while these internal processes unfold, the galaxy continues its long orbit through the universe. The Milky Way itself is not standing still within space. It moves through the local group alongside Andromeda and dozens of smaller galaxies. Together, this group drifts through an even larger structure known as the Virgo supercluster. Beyond that lies an even greater cosmic web of galaxies and clusters, stretching across hundreds of millions of light years. Within this vast cosmic web, gravity pulls galaxies along enormous filaments of matter. These filaments connect clusters like threads in a gigantic network. The entire structure slowly evolves as galaxies merge. Clusters grow, and matter continues to flow through the universe. Even on these colossal scales, subtle motions exist. Clusters drift. Galaxies fall toward dense regions of gravity. Small rotations appear within these massive systems. The universe is full of movement, from the smallest rotating planets to the largest rotating structures in existence. Yet from our quiet vantage point on Earth, these motions remain almost invisible. We see the stars as steady points of light. The sky appears calm and unchanging. Night after night, the same constellations rise and set. But hidden within that calm appearance is a universe constantly in motion. Galaxies turning slowly in the darkness. Stars tracing enormous paths around unseen centers. Gravity shaping matter across distances so vast that light itself takes millions of years to travel between them. And within this vast rotating universe, our own planet continues its gentle spin. Every 24 hours, the Earth turns once on its axis. This simple motion brings the stars into view each night. The night sky becomes a window through which we glimpse the quiet spinning of the cosmos. Above us, the Milky Way slowly turns. Beyond it, billions of other galaxies rotate as well, each one carrying its stars through graceful orbits that may last longer than the entire history of our species. The universe is filled with these slow cosmic dances, galaxies spinning silently across billions of years, stars drifting through spiral arms of glowing light. And deep within one of those arms, our small solar system continues its long journey around the center of the Milky Way, carried along by the quiet rotation of the galaxy itself. If we continue thinking about this immense motion, it becomes clear that spinning galaxies are not just beautiful structures in space. They are records of cosmic history. Every orbit traced by a star carries information about how the galaxy formed, how it grew, and what kinds of events shaped it over billions of years. astronomers can learn a surprising amount simply by studying the motion of stars. By measuring how far stars move at different distances from the centre of a galaxy, scientists can map the galaxy's gravitational field. From that map, they can estimate how much mass the galaxy contains. They can also determine how that mass is distributed. Sometimes these measurements reveal hidden features, regions where dark matter may be concentrated, areas where past mergers have altered the structure of the galaxy, or streams of stars left behind by smaller galaxies that were absorbed long ago. These stellar streams are like faint footprints in space. They stretch across the halo of the galaxy as long ribbons of stars. Each ribbon marks the path of a small galaxy that once orbited the Milky Way. Over time, tidal forces pulled that smaller galaxy apart, scattering its stars into elongated trails. Even though the original galaxy is gone, the stars remain, quietly orbiting the Milky Way along similar paths. By studying these streams, astronomers can reconstruct the history of our galaxy's growth. They can identify ancient mergers that happened billions of years ago. They can trace how the Milky Way gradually became larger by absorbing smaller neighbours. In this way, the motion of stars becomes a kind of archaeological record, a story written not in words but in the paths of billions of stars moving through space. The rotation of galaxies also helps astronomers understand the mysterious nature of dark matter. When scientists measure how far stars orbit far from the centre of a galaxy, they often find that those stars move faster than expected. If only visible matter were present, the outer stars should drift more slowly. Instead, their speeds remain surprisingly high. This suggests that large amounts of unseen mass are present in the outer regions of galaxies. Dark matter halos extend far beyond the visible edges of galaxies. Their gravity influences the motion of stars, gas clouds, and even entire satellite galaxies. Without dark matter, many galaxies might not remain stable. Their outer stars might slowly escape into intergalactic space. Instead, the invisible halo acts like a vast gravitational anchor. It holds the galaxy together as it spins. And yet, despite decades of research, dark matter itself remains mysterious. Scientists know it must exist because of its gravitational effects, but they still do not know exactly what it is made of. Various theories suggest that dark matter could consist of unknown particles that interact very weakly with ordinary matter. These particles would pass through stars, planets, and even our own bodies without being noticed. They would not emit light or absorb it, but their collective gravity would shape the structure of galaxies and clusters across the universe. In many ways, the spinning of galaxies is one of the strongest clues pointing toward the existence of dark matter. Without it, the observed motions of stars would be extremely difficult to explain. And so, the quiet rotation of galaxies continues to guide scientists toward deeper questions about the universe. Questions about the nature of matter. Questions about gravity. Questions about how cosmic structures formed and evolved. But even beyond these scientific mysteries, the spinning of galaxies carries a sense of quiet elegance. Across billions of light years, countless galaxies turn slowly through space. Some rotate gracefully with the delicate spiral arms. Others drift as enormous elliptical clouds of stars. Each galaxy moves according to the same fundamental laws of physics. Gravity pulls matter together. Motion carries it forward. Balance emerges between these forces. And from that balance, the universe creates structures of extraordinary beauty. A spiral galaxy seen from afar looks almost like a living thing. Its arms curve gently around the center. Clusters of stars sparkle along its spiral paths. Dust lanes wind through the glowing disk like dark rivers, all of it rotating slowly over hundreds of millions of years. Yet inside that immense system, individual stars follow their own quiet journeys. Some stars orbit close to the center. Others travel in wide paths near the outer edge of the galaxy. Some drift through the halo high above the galactic plane. Each star moves according to gravity's invisible guidance. Together, their combined motion forms the grand rotation of the galaxy itself. And somewhere within that enormous rotating disk, inside a small spiral arm called the Orion Arm, lies our solar system. Our sun is just one star among hundreds of billions in the Milky Way. It quietly follows its orbit around the galactic center, taking hundreds of millions of years to complete a single circuit. As it moves, it carries along the planets that orbit around it. The Earth rides along on this long journey. For every orbit the Earth makes around the Sun itself moves millions of kilometers through the galaxy. Over the course of a year, our entire solar system travels vast distances through the Milky Way. Yet the motion is so smooth and steady that we never notice it. From our perspective on Earth, the stars appear almost perfectly still. They rise and set each night as our planet rotates. Constellations shift slowly through the seasons as the Earth orbits the Sun. But the deeper motion of the galaxy remains hidden from everyday experience. Only through careful observation and measurement have astronomers uncovered the truth. The galaxy is spinning. The stars are moving. And our own solar system is quietly travelling along one of those immense galactic paths. If we could step outside the galaxy and watch its motion unfold over billions of years, we would see a majestic cosmic dance. Spiral arms slowly sweeping around the centre, stars drifting through glowing lanes of gas and dust. And far beyond, other galaxies turning in their own silent rotations, scattered across the vast darkness of space. If we allow our minds to wander even farther, beyond individual galaxies and their graceful rotations, we begin to see that motion exists everywhere in the universe. Nothing is truly standing still. Every structure, from the smallest to the largest, carries some form of movement. Planets spin on their axes. Moons circle their planets. Stars rotate slowly as they burn through their nuclear fuel. And galaxies drift and spin through the immense emptiness between them. Even the universe itself is expanding. Space is slowly stretching, carrying galaxies farther apart over billions of years. This expansion began in the earliest moments of cosmic history, and it continues even now. Yet despite this outward expansion, gravity continues pulling matter together in certain regions. Where matter gathers, structure forms. Clouds collapse. Stars ignite. Galaxies take shape. And within those galaxies, rotation emerges naturally from the motion of collapsing gas. In many ways, spinning galaxies are simply the natural outcome of gravity, working within a universe that was never perfectly still. Tiny motions present at the beginning were enough to create the vast rotating systems we observe today. What began as faint currents in the early cosmic gas eventually became the sweeping spiral arms of galaxies. Those arms now contain billions of stars. Many of those stars have their own planetary systems. Around some of those planets, there may even be observers looking up at their own night skies. From their worlds, the sky might look very different from ours. Their constellations would be unfamiliar. Their view of the Milky Way might reveal a different angle of the galactic disk. Yet the underlying motion would be the same. Their star would orbit the center of the galaxy. Their galaxy would spin slowly through space, and their planet would turn gently beneath their feet. The quiet rotation of the cosmos would still surround them. Perhaps they too would wonder why galaxies spin. Perhaps they would build telescopes and study the motions of distant stars. Perhaps they would discover the same physical laws that govern the universe everywhere. Gravity would guide their understanding. The conservation of angular momentum would explain how rotating systems form. And dark matter might still reveal itself through the motion of stars in their galaxy. Because the laws that shape spinning galaxies are universal. They apply everywhere in the cosmos. From the smallest rotating asteroid to the largest clusters of galaxies. Across billions of light years, the same principles guide the motion of matter. Yet despite this universality, every galaxy still develops its own character. Some grow large spiral arms that stretch elegantly across their disks. Others become smooth elliptical galaxies filled with ancient stars. Some galaxies ignite brilliant bursts of star formation. Others remain quiet and dim. These differences arise from the unique histories of each galaxy. The collisions they experienced, the gas they gathered, the dark matter halos in which they formed. Each galaxy carries the memory of those events within its structure and motion. The direction and speed of its rotation can reveal clues about past mergers. Distortions in its disk may hint at gravitational encounters with nearby galaxies. Streams of stars may trace the remains of smaller galaxies that were absorbed long ago. By studying the way galaxies spin, astronomers can uncover these hidden stories. They can reconstruct the events that shaped galaxies across billions of years. In this way, rotation becomes a kind of cosmic archive, a record of how matter flowed through the universe, a record of how galaxies assembled from smaller pieces, a record of the quiet gravitational forces that sculpted the cosmos. And as telescopes grow more powerful, astronomers are able to observe galaxies farther away than ever before. Because light takes time to travel, looking deeper into space also means looking farther back in time. Some of the galaxies we observe today appear as they were billions of years ago, when the universe was still young. These distant galaxies often look very different from the ones nearby. Many appear smaller and more chaotic. Some have irregular shapes with intense bursts of star formation. Others are still in the process of merging with neighbours. Their rotations are not yet as smooth or organised as those of mature spiral galaxies. Over time, these young galaxies gradually evolve. Their chaotic motions settle. Disks begin to form. Rotation becomes more orderly. Spiral arms emerge. The galaxies we see in the nearby universe are the result of billions of years of this slow cosmic evolution. They represent a later chapter in the story of galaxy formation, a chapter in which rotation has become one of the defining features of many galaxies. And yet the process continues. Even now, new stars are forming inside galaxies. Small galaxies are merging with larger ones. Gas clouds are collapsing into fresh stellar systems. The universe is still building and reshaping its galaxies. Their rotations continue. Their structures evolve. And their stars travel along vast orbits that may last longer than the entire existence of our species. When we look up at the night sky, we are seeing only a tiny fraction of this immense cosmic motion. Most of the stars visible to our eyes belong to our own galaxy. Their quiet light reaches us from distances of hundreds or thousands of light years. Beyond them lie countless other galaxies too faint to see without telescopes, each one spinning slowly through the darkness of space, each one carrying billions of stars along its graceful rotation. And within that vast rotating universe, our own small world continues its journey, quietly orbiting the Sun as the Sun itself circles the centre of the Milky Way. And so, the next time you look up at the night sky, it may feel calm and perfectly still. The stars appear fixed in place, quietly shining in the darkness. But beyond that peaceful view lies a universe filled with motion. Stars orbiting the centres of galaxies, galaxies slowly spinning through space, and vast cosmic structures drifting across the expanding universe, all of it moving according to the same simple laws of gravity and motion, shaping the grand structures we see across the cosmos. Our own solar system is part of that motion as well. The Earth spins gently beneath our feet, circles the Sun once each year, and the Sun itself continues its long journey around the centre of the Milky Way, carried along by the quiet rotation of our galaxy. Everything is moving. Everything is part of the same cosmic dance. And yet, from our small place on Earth, beneath the calm glow of the stars, the universe still feels peaceful and still. Perhaps that is part of its beauty. A universe filled with motion, but moving slowly enough that we can pause, look up, and simply wonder. If you enjoyed this quiet journey through the cosmos, consider subscribing to the channel. There are many more calm explorations ahead, gentle stories about space, science, and the mysteries of the universe, designed to help your mind slow down and drift peacefully into rest. And if you'd like to continue exploring the universe tonight, you may enjoy another video from the Sleepy Scientist. Until then, thank you for spending this quiet moment among the stars. And wherever you are in the world, may your night be calm, peaceful, and full of wonder.